So the first thing we need to do before we get into stoichiometry with energy is review a little bit of calorimetry. I will link a CK12 page to this in case you need more review than we're going to do in this little video here. But think all the way back to probably about the first month or so of Chemistry 1. That's when we talked about calorimetry. You know, we did the heating and cooling curves and talked about water, all those constants, and figured out how much energy it took to do certain changes. And then at the end of that, we came to this understanding: the conservation of energy. The heat lost by one system is equal to the heat gained by another system. And so for calorimetry, one of those systems is usually water, and the other system is whatever we're studying. And so the calorimeter is just some kind of container, a system, an insulated chamber in which a substance, which, like I said, it's usually going to be water. We're only going to use water because we know the specific heat capacity of it. It absorbs or it releases energy to tell us what's happening with the other one. So I can measure the heat loss or the heat gain by water, whichever way the reaction is actually going. If it's endothermic or exothermic, water will be one or the other. And then I can figure out exactly the amount of energy that the water gained or lost by using math, using this equation here that we're going to get to, Q equals MC delta T. So from that amount of temperature change, energy gained or lost can be calculated. And hopefully you remember this equation. Q is energy, and the energy is going to be measured in joules. That's what the J stands for. M is the mass in grams, because heat depends not just on temperature but also the amount of the substance. C is the specific heat constant for water. That is 4.18 joules for every gram in degrees Celsius. That is the unit for specific heat constants. And notice this is a delta T. So that is temperature change. It's not the temperature. It's the difference between the initial and the final temperature. You can use Celsius for this one. You could also use Kelvin. It really doesn't matter because we're looking at the difference. And so usually we just use Celsius because that's convenient. That's what we usually measure in. Now, if that doesn't make sense to you, here's my lovely artwork that may or may not help. But basically what's going to happen with these problems that we're going to look at, if you want to think about it that way, when we did this before, we actually did a lab also, and you had like pieces of metal, and we were trying to figure out the specific heat constant of the metal. But in this case, we've actually got a reaction happening. So this is your insulated chamber. We're going to have a lid on this, not much space, hopefully, between the top of the water and the lid. We've got a thermometer to measure the temperature of the water, and the reaction is going to happen here. So if that reaction is exothermic, it's going to release energy, and it's going to cause this water to heat up. So the temperature is going to rise, and I can monitor that. If this reaction is endothermic, it's going to absorb energy from the water, and the temperature of the water is going to decrease. And so, again, this insulated chamber just hopefully prevents energy being lost to the surroundings beyond the calorimeter. Obviously, it's not a perfect system. You're always going to have a little bit of heat escaping, but this is insulated so that we can minimize that source of error. I'm just going to do one little quick problem with you on this because we're going to be looking at some other examples that are more in context of how you're going to see them with your problems. But you may, and this is very general, so a reaction, we don't even care at this point what the reaction is. A reaction occurs in a calorimeter which contains 150 milliliters of water at 23.6 degrees Celsius. So 150 milliliters here. At the conclusion of the reaction, the water's temperature is 47.8 degrees. So the temperature's gone up. That tells me that the reaction that happened is exothermic. So how much energy is released, again, exothermic, by this reaction? So in this case, the energy gained by the water is equal to the energy released during the reaction. And so I can calculate that given the information that I have here. So my formula for that is Q equals MC delta T. This is going to be for the water. And the reason it's for the water is because I know a specific heat constant for the water. I don't even know what the reaction stuff is. All right. So if I'm looking for energy, that's my Q. So I look for the mass of the water, which is 150 milliliters. That's our mass. But I know from what we were doing with solutions before that water's density is 1 gram per milliliter. So if it gives me milliliters, it's really also giving me grams. So 150 milliliters is the same as 150 grams. Again, that only works for water, and that's a good reason to use water for these calculations. So 150 grams is my mass. The specific heat constant for water, I'll give you this on a test. It's 4.18 joules per gram in degrees Celsius. But hopefully that rings a bell from what we were doing before, way back in Chemistry 1. And I need a delta T, a change in temperature. So it ended up at 47.8 degrees. It started out at 23.6 degrees. So I'm just going to subtract and see that my temperature change is 24.2 degrees Celsius. All right. So, calculator. Just plug and chug. 150 times 4.18 times 24.2 is 15,173.4. 4 sig figs, 3 sig figs, so I'm going to round to 3 sig figs. So that's 15,200 joules. And that is your energy. Now I'll mention one more thing. Lots of times these numbers that we're going to look at are in kilojoules. So that's just changing this by a factor of 1,000. So I've moved my decimal to go from joules to kilojoules 3 places to the left. So this is the same as 15.2 kilojoules. Now, again, this is energy that is gained by the water, which means it's released by the reaction. So this just says how much energy was released by this reaction. This answer is fine. But if we're talking about the delta H for that reaction, that's going to be negative. Because remember, all of these changes, we look at them in terms of, or from the point of view of the system. So the reaction actually lost 15.2 kilojoules of energy. So again, that's a quick review of calorimetry. I'll link the CK12 page if you need a little more information. But we're going to continue to use this through some other examples. So I will be talking to you soon.